Assalamualaikum warahmatullahi wabarakatuh. So today our group want to present about chapter 5 for PHY370, which is about X-ray diffraction technique. Basically, our group consists of 3 students, which is Rabiato, Shakila and Shamira from AS1205J. The learning outcome that students should be able to know is what is diffraction of X-ray, X-ray sources, and students also know how to do a calculation about displacing. So this is the subtopics that you will learn in this chapter. Before we proceed to the first subtopic, we need to know who's the first person that has found X-ray. Wilhelm Conrad Röntgen, he is the first person that discovered X-ray in 1895. According to Röntgen, he noticed crystal near a high voltage cathode ray tube exhibit a fluorescent glow even when he shielded them with dark paper. Some form of energy was being produced by the tube that was penetrating the paper and causing the crystal to glow. He called the unknown energy as X radiation. Do you know what is diffraction? Diffraction is the slight bending of a wave as it passes around the edge of an obstacle or passes through a narrow slit. And you can refer to the figure at the right side of your screen to imagine about how it works. Diffraction not just occurs in sound or water wave, but it also occurs in electromagnetic wave, such as light and radio wave. For the light diffraction, it happens due to the light bending around the edge of an object. The interference pattern of bright and dark lines from the diffraction experiment can only be explained by the additive nature of wave. There are 2 types of interference that you already learned in the last semester. So what is the 2 types of it? The first one is constructive interference and the second one is destructive interference. Both of it have some differences, and the most common differences is the interference pattern. For the constructive interference, it will result of synchronous light waves that add together to increase the light intensity where the 2 waves must be in phase. And for the destructive interference, it resulting in darkness when 2 out of phase light waves cancel each other out where the 2 waves must be out of phase. You can look at the graph of both interference to know the meaning of wave in phase and wave out of phase. So you must wonder why is the type of interference that X-ray use. So X-ray diffraction is based on the constructive interference of monochromatic X-ray and a crystalline sample. These X-rays are generated by a cathode ray tube then filtered to produce monochromatic radiation, collimated to concentrate and directed toward the sample. The interaction of incident rays with the sample produce constructive interference when conditions satisfy Bragg law. Since you have known about the diffraction and interference, so now we proceed to the differences between them. Diffraction occurs in the disk, which is when you look at the disk, you will see the rainbow pattern. And interference occurs in bubble of soap when it illuminated by a light source and reflects a spectrum of colors. Other differences is the intensity of all the secondary maxima in diffraction is not equal, but in interference, the intensity of all bright bands is equal. The width of central maxima is large in diffraction, and for interference, the width of all the interference fringe is equal. Also in diffraction, the intensity of secondary minima is not completely zero, but in interference, the intensity of dark fringe is completely zero. Next, what is the properties of X-ray? X-ray is the invisible, highly penetrating electromagnetic radiation of exactly the same nature as light, but have shorter wavelength, about 10 power of negative 8 meter to 10 power of negative 11 meter. It also needs a high voltage in order to produce X-ray. X-ray also travel in a straight line and do not carry any electric charge, and they also capable to travel in a vacuum condition. How do X-ray work? X-ray are produced when high velocity electrons collide with the metal plate and giving the energy as X-ray. The X-ray beam are travel through the air and comes in contact with the body tissue and produce an image on a metal film. Soft tissue like organs, skin, cannot absorb the high energy rays and the beam just passes through them, but the dense material inside our body, such as bones, it will absorb the radiation. And the figure is shown when your hands are exposed to the X-ray. It will develop on the X-ray film depends on the area that has been exposed to the X-ray. The white area show the denser tissue like bones which have absorbed the X-ray, and the black areas on the X-ray film represent the area which X-ray have passed through the soft tissue. Next slide, we go to the production of X-ray. X-ray are short wavelength of electromagnetic radiation produced by the deceleration of high-energy electron and also produced by the electronic transition of electron in the inner orbital of atom. X-ray can be produced in an X-ray tube that highly evacuated glass bulb. It contains two electrodes, which is an anode and a cathode. So, how this tube can produce an X-ray? At first, a current is passed through the tungsten filament and heats it up. As it is heated up, it will increase the energy, that resulting electron to be released from the filament. Then, the electrons are attracted towards the positively charged anode and hit the tungsten target with a maximum energy determined by the tube potential. As the electron bombard the target, they interact via Bremsstrahlung and characteristic interaction, which result in the conversion of energy into heat and X-ray photons. The X-ray photons then are released with a range of energy out of the window of the tube and form the basis for X-ray image formation. For the next production of X-ray is by electronic transition of electron in the inner orbital of atom. It's happen when a bombarding electron strikes a K-shell electron out. Then the bombarding electron diverted. Electron that's hit ejected as a photon electron and absorbed. Then outer shell electron more down to fill the ejected electron space. The energy from this is released and as a characteristic energy photon. For the X-ray diffraction in crystal, in 1920, it was discovered by Max von Loo when he noticed that if a beam of X-ray passes through a crystal, diffraction will take place and a pattern will be formed on a photographic plate that placed at a right angle to the direction of the rays. The discovery have provided a new method for investigating the fine structure of matter. And yes, one of the best methods to determine the crystal structure is by X-ray diffraction. In macromolecular X-ray diffraction experiment, an intense beam of X-ray strikes the crystal of study. In general, crystal diffracts the X-ray beam differently depending on its structure and orientation. The diffracted X-ray is collected by an area detector. The diffraction pattern consists of reflection of different intensity which can be used to determine the structure of the crystal. In 1913, Sir William Henry Bragg and his son developed a relationship to explain why the cleavage phase of crystal appear to reflect X-ray beam at certain angle of incidence. Although Bragg law was used to explain the interference pattern of X-rays scattered by crystal, diffraction has been developed to study the structure of all states of matter with any beam. Bragg carried out a series of experiments, the result of which he published. The Bragg equation is 2d sin theta equal to n lambda. Bragg law refers to the simple equation which is 2d sin theta equal to n lambda. Bragg law can easily be derived by considering the conditions it is necessary to make the phase of the beam coincide with the incident angle equal and reflecting angle. The incident rays are always in phase and parallel up to the point at which the top beam strikes the top layer at atom Z. You can refer to the figure below. The second beam continues to the next layer where it is scattered by atom B. The second beam must travel the extra distance of AB plus BC if the two beams are to continue traveling adjacent and parallel. This extra distance must be in integral multiple with the wavelength. for the phase of the two beams to be the same. So based on this, the first equation before you get Bragg law, Bragg equation is AB plus BC equal to n lambda. We can use trigonometry to relate between d and theta to the distance AB plus BC. Since the distance AB is opposite to theta, so the next equation will be AB equal to d sin theta. Because of AB is equal to BC, so the equation 2 becomes 2AB equal to n lambda. Substitute equation 3 in 4, so you will get 2d sin theta equal to n lambda, and Bragg law has been derived. And this is the example of Bragg law simulator that you can try by your own so that you will understand more about this topic. So we click on the first link here. And this is how it looks like. And I think it's quite interesting for you guys to explore. This simulator shows two rays of incident on a two atomic layer of a crystal that's separated by the distance, which is d. The simulator begins with the scattered rays are in phase and interfering constructively. Okay. You look at here and note that the peaks and through on the beam are aligned, which is same, and it will making a constructive interference. Okay, you can adjust the wavelength, the distance, and also the theta. So now we adjust the wavelength to say distance also 6. And theta is still 30. As you can see here, it's also give it to you the calculation of n, integer n, and it also give you what type of interference this wave, and means it show the constructive interference. So this wave obey to the Bragg law. What happen if you change the lambda to the 4.7 and it shows to you the destructive interference? Means that it's not obey the Bragg law. I have prepared two questions regarding this topic. The first question is: X-ray with wavelength of 125 picometer was used to study a crystal which produced a reflection at an angle of 17.4 degree. Assuming first order diffraction, what is the distance between planes of atom? So you just use this equation 2d sin theta equal to n lambda and put all the information given in this equation, and then you get d is about 2.09 times 10 power of negative 10 meter. The next question is: crystal XYZ has an interplanar spacing of 94.3 picometer. Using first order diffraction, what is the X-ray wavelength that should be used to produce a reflection with an angle of 19.5 degree? So also same like the previous question, you just use 2d sin theta equal to n lambda, and then for n lambda you will get 62.96 picometer.
Another subtopic for X-ray diffraction technique is calculation of this spacing. From the previous slide, we have learned about Bragg's law equation, which is 2d sin theta equal n lambda, where d is the spacing of the plane and n is the order of diffraction. So now, what is the d spacing and where is it come from? This figure shows where the spacing come from. X-ray incident at an angle theta on one of the plane of the set. There will be constructive interference of the wave scattered from two successive lattice point A and point B in the plane if the distance AC and DB are equal. Next, construct this interference of waves scattered from same plane. If the scattered wave made the same angle to the plane as the incident wave, the diffracted wave looks as if it has been reflected from the plane. We consider the scattering from the lattice point rather than atom because it is the basis of atom. Associated with each lattice point, there is the true repeat unit of the crystal. The lattice point is analog of the line on optical diffraction grating, and the basis represents the structure of the line. For diffraction maximum, coherent scattering from a single plane is not sufficient to obtain a diffraction maximum. It is also necessary that successive planes should scatter in phase. This will be the case if the path difference for scattering of two adjacent planes is an integral number of wavelengths. Next subtopic is cubic crystal structure determination. As we know, Bragg's law X-ray diffraction is a technique of the determination of crystal structure. Labeling the reflection plane is the first step. Using the Miller indices, a beam corresponding to a value of n more than 1 can be written as the n-order reflection from the HKF planes. For example, third-order reflection from 111 planes will reflect 3 of the reflection. Second, the n-order diffraction of HKF plane. The Bragg's law, which is 2d over n sin theta equal lambda. N-order diffraction of HKF plane of d spacing will look the first order of spacing d over n. The final is that NH, NK, NL is reducing spacing, known as the final answer, known as NH, NK, NL when reflection in Miller indices. General equation for Bragg's law: 2d sin theta equal to n lambda, where n is an integer and refer to the reflection order. For example, for Couperin K alpha radiation is lambda equal to 1.54 angstrom and D110 is 2.22 angstrom. This table shows an example n sin theta, theta, and the description. The general equation of Bragg's law in crystal structure determination is D equal to A over square root h squared plus k squared plus l squared. The Bragg's law that applies to all sets of crystal plane for cubic structure, so the smaller spacing, the higher the angle of diffraction. The spacing of the peak in the diffraction pattern is inversely proportional to the spacing of the plane in the lattice. The diffraction pattern will reflect the symmetry properties of the lattice. Let's try first example. A sample of body center cubic metal was placed in an X-ray diffractometer using X-ray with a wavelength of lambda equal to 0.1541 nanometer. Diffraction from the 110 plane was obtained at 2 theta equal to 44.704 degree, and the question is calculate a value for the lattice constant A for this body center cubic elemental metal. Assume first order diffraction n equal to 1. So what we are going to do is we are going to use Bragg's law, which is relating the wavelength. We are given 2 theta, so the theta must divide by 2. Substitute all the information given, we will get value of D. The interplanar spacing in cubic material is given by D equal to A over square root h squared plus k squared plus l squared. So substitute the value of D in this equation, and then we get the answer of A equal to 2.865 times 10 power of negative 10 meter. Example 2. The wavelength of the X-ray is 0.071 nanometer, which is diffracted by a plane of source with 0.28 nanometer as the lattice constant. Determine the glazing angle for the second order diffraction. Assume the value of the plane of source to be 110 and the given source is Bragg. Again, we use Bragg's law equation. 2D sin theta equals n lambda. We know that Bragg has the phase center cubic. Therefore, D equals A over square root h squared plus k squared plus l squared. Substitute all the value given, and then we get value of D equal to 0.198 meter. The last step is substitute value of D in the Bragg's law equation. Then we get the answer of glazing angle is 21 degrees.
I will present about scanning electron microscope and infrared spectroscopy. Okay, what is scanning electron microscope? Scanning electron microscope is one type of electron microscope that uses the beams of electron to scan the surface of microorganisms. In recent years, scanning electron microscope become powerful and versatile tools for material characterization. This is because the size of materials used in various applications continues to shrink. This scanning electron microscope works on the principle applying kinetic energy to produce signals by the interaction of electrons. Types of signals being produced by SEM. As we can see through the diagram, electron beam from the source incoming primary electrons. It hit the sample, and as a result, it produced 5 signals. The signals are X-rays, secondary electrons, Auger electrons, backscatter electrons, and cathodoluminescence. Okay, this is the schematic diagram of SEM. Basically, the electron being ejected from the electron gun that will passing through the anode, condenser lens, objective lens, and received by the detectors. So, let's watch a video about the working of SEM.
Working of scanning electron microscope. In this video, we are going to see about working of scanning electron microscope. Internal parts of scanning microscope: electron gun, anode, condenser lens, objective lens, X-ray detector, secondary detector. A high-energy electron beam is produced by an electron gun. The beam is focused to a spot of about 100 angstrom diameter and made to scan the surface of the specimen. The scintillator collects the secondary or scattered electrons and converts into light signal. Backscatter electrons reflects to the surface and deeper from the specimen is also known as reflected electrons.
So this is the example of the image that being produced by scanning electron microscope. Okay, the advantages and limitation of SEM. The advantages: it is easy to operate, it is used in a variety of industrial applications, and it is able to generate digital data. It is easy to acquire data. So for the limitations, it is very expensive, it is bulky to carry. Also, they must be used in rooms that are free of vibrations and free of electromagnetic elements. They must be maintained with a consistent voltage, and lastly, they should be maintained with access to cooling system. Okay, we go to the next subtopic, infrared spectroscopy. What is IR? IR is the analysis of infrared light interacting with a molecule. This can be analyzed in three ways by measuring absorption, emission, and reflection. The main use of this technique for organic and inorganic chemistry. It being used to determine the functional groups in molecules. FTIR is one of the instruments for IR spectroscopy. Function of FTIR is an analytical use to identify organic, polymeric, and in some cases inorganic materials. Another function of FTIR, it could identify and characterize unknown materials like films, solids, powder, or liquids. Next, it also can identify contamination on or in material like particles, fibers, powders, or liquids. Okay, this is the schematic diagram of FTIR. Okay, we can see the light source traveling from beam splitter, moving mirror, fixed mirror, interferometer, sample, detector, and for the spectrum. The function of interferometer, it is a special instrument that can read IR frequency simultaneously. So, let's watch a video about the working IR. So the advantages and limitation of FTIR. It is better in sensitivity and brightness, high wave number accuracy. It will save our times, enhance frequency resolution. Data can be stored and reanalyzed. For the limitations, it is expensive, require precision for mirror movement, and detection of compound is influenced by water vapor, path length, and chemical interference. That's all from me. Thank you.